Picture this: a brand new aircraft, 3 experienced pilots, and 228 people crossing the Atlantic on a clear night. In less time than it takes to brew a cup of coffee, just under 4 minutes, that aircraft went from a routine cruise at 35,000 feet to the bottom of the ocean. No explosion, no fire, no mechanical failure. So what exactly happened up there? On the 28th of May 2009, 3 Air France pilots landed in Rio de Janeiro following a westbound flight from Paris. Ahead of them was a 3-day layover before they would ferry the return leg home aboard Air France Flight 447. What we know about how they spent those days is limited, but there are clues. The youngest of the 3, a 32-year-old first officer, had brought his wife along for the trip. It's reasonable to assume he wasn't spending his evenings resting in a darkened hotel room. The flight was scheduled to depart Rio at 11 p.m. local time, which translated to 2 a.m. Paris time. By the time they were due to land back in France, their bodies would have been fighting the clock for over 12 hours straight, pushing deep into what aviation physiologists call the circadian trough, the window of night during which human alertness and cognitive performance hit their lowest point. Because of this, Air France had augmented the standard 2-pilot crew with a 3rd aviator, allowing each pilot to rotate off and rest during the flight. The captain was 58 years old, with over 11,000 total flight hours, including 1,700 in command of the Airbus A330. Experienced, respected, and trusted with the route. The first officer, the least experienced of the group, had 3,000 hours in total and had only completed his A330 type rating the year before, in 2008. He would be designated as pilot flying for the overnight crossing. The 3rd crew member, a relief pilot and senior first officer aged 37, had logged 6,500 hours total and was actually the most experienced on the A330 specifically, with 4,500 hours on type. However, he had barely flown in the 3 months prior to the trip, partly because he had been working in an administrative management role for the airline. His hands-on sharpness may not have matched his logbook. Before the crew walked out to the aircraft, they gathered around the pre-flight planning documentation, weather charts, fuel calculations, and flight plans. The departure from Rio was clean. Paris looked fine, but the middle of the route was a different story. Flight 447 would be crossing the equator over the mid-Atlantic, and that meant threading through a region called the Intertropical Convergence Zone, the ITCZ. This is where the trade winds from the northern and southern hemispheres collide, forcing warm, humid ocean air rapidly upward. The result? A band of violent thunderstorms that can tower up to 60,000 feet, nearly double what most commercial jets can reach. Navigating through the ITCZ is a fact of life on transatlantic routes that cross the equator. Pilots are trained for it. But there's a particular trap that these ocean storms set. Because they form over water rather than land, the moisture content inside them can be lower than the radar signature suggests. That makes them harder to see and easier to accidentally fly into. More critically for this story, deep inside these towering storm cells, water droplets are hurled upward by powerful internal currents into regions of extreme cold. Those droplets become supercooled, meaning they remain liquid at temperatures far below freezing. The moment they contact a surface, say a sensor on the nose of a plane, they freeze instantly. But it gets more complex. When these supercooled droplets collide with ice crystals already inside the storm, they can form a soft, pellet-like material. Not quite hail, not quite snow, something in between, and something that arrives in enormous volume. It hits an aircraft like a sustained wave of tiny projectiles, and it can overwhelm specific components on the aircraft in seconds. The year before this accident, Air France had already reported more than 9 separate incidents where this exact type of precipitation had clogged up critical sensors on their fleet. Safety bulletins had been distributed. The problem was known. Here's where we need to step back for a moment, because what follows cannot make sense without understanding a few things about how modern airliners actually work. Pitot tubes. Pilots don't have a speedometer the way your car does. Instead, aircraft measure speed by comparing 2 types of air pressure. Pitot tubes, small, electrically heated probes mounted along the fuselage, capture the total pressure of oncoming air. Static ports, mounted flush to the aircraft skin, measure the ambient air pressure around the plane. The difference between these 2 values gives you airspeed. These systems feed into computers called air data modules. And because airspeed and altitude are so fundamental to safe flight, there are 3 completely independent sets of probes and computers doing this calculation simultaneously. The pitot tubes are heated to prevent ice buildup. But as the 2008 incident report showed, under certain conditions involving high-altitude ice crystal storms, that heating isn't always enough. Fly-by-wire and the laws of flight. The Airbus. A 330 is a fly-by-wire aircraft. When a pilot moves their side stick, the small joystick-style controller that replaces a traditional yoke, that input doesn't physically move the control surfaces. Instead, it sends an electronic signal to a computer, which interprets the command and moves the hydraulic actuators accordingly. This system comes with a crucial advantage: flight envelope protection. As long as all 3 air data computers are in agreement and feeding the flight computer's reliable data, the aircraft operates in what Airbus calls normal law. In this mode, the aircraft simply will not let itself be stalled. It won't allow extreme bank angles. It won't exceed its maximum speed. The computers essentially act as a safety net beneath the pilots. But here's the catch, and it's an important one. Those protections only work when the computers are confident in the data they're receiving. The moment 2 or more air data computers start contradicting each other, the flight computers no longer know what's real. In that situation, they do exactly what you'd expect a machine to do when it's uncertain. They step back. The aircraft degrades from normal law into what's called alternate law. And in alternate law, the stall protection disappears. The bank angle protection disappears. The aircraft becomes, in a very real sense, a conventional aircraft, one that can be stalled and pushed into an unusual attitude if the pilot makes the wrong inputs. There's one more thing about alternate law that matters enormously here. The side stick no longer commands a stable roll rate. Instead, it commands the control surfaces directly. At altitude, where the thin air provides almost no aerodynamic damping, this makes the aircraft significantly more sensitive and harder to control. Small inputs create large, fast responses. The trim problem. On a conventional aircraft, pitch trim is something a pilot manages manually. You feel the forces through the yoke. You notice when the aircraft wants to pitch up or down and you adjust. In the Airbus, pitch trim is automatic. When the pilot holds a nose-up attitude, the horizontal stabilizer, a massive surface at the tail, gradually moves on its own to maintain that attitude without the pilot having to hold pressure. This is seamless and comfortable in normal law. But in a degraded flight state, at an extreme nose-high attitude, that automatic trimming can quietly move the stabilizer to its maximum nose-up position. And once that happens, even a pilot who finally recognizes the situation will find the aircraft extremely resistant to pitching forward again. Here's something that the final accident report highlighted in stark terms. Air France had included unreliable airspeed scenarios in their recurrent simulator training during the years leading up to the accident. Pilots practiced what to do if the speed indications suddenly became invalid, but almost all of that training was conducted at low altitude. That's understandable from a prioritization standpoint. At low altitude, close to the ground, an error is immediately catastrophic. But it had an unintended consequence. The lessons trained into these crews were anchored to low-altitude performance, where the engines are powerful relative to the aircraft's weight and where the speed margins are more generous. At 35,000 feet, the rules change dramatically. The engines can barely maintain level flight, let alone pull the aircraft out of trouble with raw power alone. The stall angle of attack, the point at which the wing stops generating lift, is reduced due to the aerodynamic effects of flying close to the speed of sound. Every margin shrinks. None of the three pilots on Flight 447 had received any recent training on high-altitude stall recognition or recovery. The last time any of them had practiced a stall was during their initial type rating years earlier in a low-altitude scenario where the lesson taught was essentially add power and the aircraft will recover. At 37,000 feet, that lesson would prove to be exactly wrong. The 216 passengers boarded without incident. The crew completed their preparations and received pushback clearance from the gate at 22:09 UTC, just 9 minutes behind schedule. The first officer took the controls as pilot flying and executed a textbook departure from Rio. The aircraft climbed smoothly, turning northeast along the Brazilian coastline before heading out over the open ocean. Somewhere above 20,000 feet during the climb, the relief pilot excused himself to begin his scheduled rest period. He made his way back to the crew bunk compartment directly behind the cockpit, 2 bunk beds in a small enclosed space, and settled in for roughly 3 hours of sleep. The 2 remaining pilots leveled off at their initial cruise altitude of flight level 350, 35,000 feet, and checked in with Atlantic Oceanic Control. Soon they would pass beyond radar coverage entirely, tracked only by periodic position reports radioed in by the crew themselves. There had been an attempt to use a new satellite-based tracking system called ADSC that would automatically broadcast the aircraft's position. But due to a formatting error in the filed flight plan, the system wouldn't connect. From the moment they left conventional radar coverage, Flight 447 was essentially invisible to the world below. As the aircraft pushed north across the equatorial Atlantic, the crew received a company message warning of significant convective activity ahead. The first officer scanned his navigation display and could see the returns building in front of them. The mood shifted. The first officer was vocal about his concern with what he was seeing. The relief pilot, who had been watching through his own display, leaned over and suggested deviating left to avoid the worst of it. At 1:59 UTC, the relief pilot arrived back in the cockpit to take over monitoring duties, while the captain prepared to go rest. The captain listened briefly to the first officer's handover briefing. Turbulence expected. They were in cloud, couldn't climb any higher, and then walked out without leaving specific instructions about handling the storms ahead. The two first officers were now alone. 4 minutes later, at 2:06 UTC, the first officer called back to the cabin crew to warn them about light turbulence ahead. Then the relief pilot, studying his weather radar on maximum sensitivity, suggested another heading adjustment to the left. They turned approximately 12 degrees and left the flight plan route. No notification was sent to air traffic control. At 2:08:17, the cockpit voice recorder captured a sudden change in the ambient sound, the sharp, percussive rattle of precipitation hitting the aircraft's skin. The first officer noticed the cockpit temperature rising and thought something had been adjusted in the air conditioning. Then came the smell, clean, sharp, electric. The relief pilot recognized it immediately as ozone, a byproduct of electrical discharge. They were inside the storm. 20 seconds later, the sound intensified into the unmistakable hiss of ice crystals striking the aircraft. The turbulence picked up. The first officer pulled the commanded speed back from Mach 0.8 to 0.80, the turbulence penetration speed. The auto throttle responded, reducing thrust. Then, at 2:10:05, everything changed. The autopilot disconnected. The auto throttle dropped offline. A cavalry charge alarm, the distinctive triple chime reserved for high-priority warnings, filled the cockpit. At the same instant, a gust rolled the aircraft sharply to the right. "I have controls," the first officer called out, reaching for his side stick. The indicated airspeed on the left primary flight display collapsed from 275 knots down to 60 knots in an instant, a clearly impossible reading. The altimeter, recalculating based on that false low speed, simultaneously showed a drop of 300 feet and a negative vertical speed. The first officer, suddenly hand-flying in the dark, with all three automation systems gone and alarms blaring from every direction, did what felt instinctive. He corrected the apparent altitude drop. He pulled back. He pulled back, and he kept pulling. With all three air data computers now feeding conflicting information, the flight computers degraded into alternate law. Stall protection gone. Bank protection gone. Roll sensitivity doubled. The aircraft began oscillating left and right as the first officer overcorrected through each bank. A brief stall warning flashed, then went quiet. The relief pilot called out, "What is that?" And it was unclear whether he understood what the sound meant. The flight directors, which should have been switched off per the unreliable airspeed procedure, instead reactivated partway through the sequence, but now commanded the aircraft to maintain its current climb rate of 6,000 feet per minute. This was not helpful. In the first 18 seconds, 10 separate ECAM warning messages appeared on the screen. The master warning and master caution lights illuminated. A continuous altitude deviation chime added to the noise. The pitch attitude reached 12 degrees nose up. The aircraft was now climbing at nearly 7,000 feet per minute, more than 7 times the normal cruise rate. Speed was bleeding away rapidly. The relief pilot noticed the pitch and called out, "What's your speed?" The first officer replied that he was going back down, but reduced the pitch only slightly. The aircraft continued to climb through 36,000 feet, then through 37,000, past the calculated maximum altitude, past the edge of what the aircraft could physically sustain. The stall warning triggered again. This time, it stayed on, a continuous, unambiguous audio alarm that would sound for the next 45 seconds. Neither pilot verbalized it. Neither pilot said the word stall. At 2:10:57, the aircraft reached its critical angle of attack and entered a fully developed aerodynamic stall. Violent, high-frequency buffeting shook the airframe, completely unlike the rolling turbulence they had felt minutes earlier. The first officer pushed the throttles to maximum takeoff thrust. At 37,000 feet, the engines couldn't save them. The aircraft reached its maximum recorded altitude of 37,924 feet, then began to fall. The first officer continued to hold the side stick, pulled fully back for much of the descent. The stabilizer had trimmed itself to maximum nose-up position, working against any recovery attempt. The aircraft fell with the nose pointed upward, while the flight path tracked almost vertically downward, a condition so extreme that the pitot tubes, now hammered by airflow arriving from nearly 40 degrees below the aircraft's nose, again lost the ability to make sense of the pressure differential. Speed indications disappeared again, and then something cruel happened. When the computed speed fell below 60 knots, the onboard logic, designed for a world where that speed only existed close to the ground, told the stall warning system to disregard the angle of attack sensors. The stall alarm went silent, not because the stall had ended, because the system had given up trying to report it. The relief pilot tried to understand what was happening. "We've got the engines. What's going on?" He got no clear answer. The captain was called back to the cockpit at 2:11:42, 1 minute and 42 seconds after the autopilot had first disconnected. He arrived to find the aircraft descending through 35,000 feet, pitch attitude swinging between 15 degrees nose up and 9 degrees nose down. 10 ECAM warnings active. No stall alarm, for reasons no one in the cockpit understood, and severe buffeting shaking the entire aircraft. "What are you doing?" he asked. "I don't know," the relief pilot answered. "I don't know what's happening." In the confusion that followed, the stall was never identified, never verbalized, never addressed. At one point, the first officer even deployed the speed brakes, indicating he believed the aircraft was going too fast. He was told to stow them immediately. The aircraft passed through 20,000 feet, then 10,000, falling at between 10,000 and 15,000 feet per minute. Near the end, with the ground proximity warning system screaming, "Sink rate, pull up," the strategy finally reversed. Both pilots pulled back together, pitching the nose 16 degrees above the horizon. Speed had decayed to 107 knots forward and 107 knots straight down. At 2:14:28 UTC, Air France Flight 447 impacted the Atlantic Ocean at a 45-degree angle and a vertical descent rate of nearly 11,000 feet per minute. The structural forces were equivalent to a free fall from the top of a 46-story building directly into concrete. All 228 people on board died instantly. On the surface, nothing changed for hours. The aircraft had passed out of radar coverage long before the accident. HF radio dropouts in this region were common and not immediately alarming. The 4 oceanic control centers that should have been in contact began exchanging calls. Had anyone heard from 447? No. 3 hours after impact, the flight was formally declared missing. 3 hours after that, the first emergency broadcast went out. 2 days later, floating debris was spotted on the ocean surface. 3 days after that, the first physical wreckage and the first victims were recovered. What followed was one of the most complex underwater search operations in aviation history. The ocean floor in the search area reaches depths of nearly 13,000 feet. The entire seabed topography had to be mapped. Multiple search campaigns were launched and suspended over nearly 2 years. It wasn't until April 2nd, 2011, nearly 2 years after the accident, that the main wreckage field was located on a relatively flat area of the seabed, about 6.5 miles from the aircraft's last known position. Among the wreckage, both the cockpit voice recorder and the flight data recorder were recovered in remarkable condition. Those 2 black boxes contained everything you've just heard. No part of this aircraft actually failed in the conventional sense. The pitot probes were overwhelmed by conditions that may have exceeded what they were certified to handle. Temporarily, for a matter of minutes, the heating elements simply couldn't keep up with the volume of ice crystals. Everything that followed was a cascade of human responses to that temporary data gap. Responses shaped by fatigue, by incomplete training, by startle, by confusion, and by deeply ingrained muscle memory that was correct in some situations and catastrophically wrong in this one. The crew never executed the unreliable airspeed procedure. The key memory items, disconnect the automatics, set a known pitch and power setting, and fly, were never applied. The initial pitch-up response, likely instinctive, led to a rapid energy loss at an altitude where the aircraft had almost no margin to give. The monitoring pilot caught it late, and the corrections demanded were too gentle. The aircraft left its performance envelope. By the time a stall had fully developed, no one in the cockpit recognized it for what it was, and the warning system itself, by its own design logic, eventually stopped reporting it. The accident sent a shockwave through the global aviation community. What followed were sweeping changes. Airlines around the world were directed to implement upset prevention and recovery training, formal, standardized modules that specifically address high-altitude stall scenarios, the aerodynamic differences that exist at cruise altitude versus approach altitude, and the counterintuitive recoveries sometimes required. New memory items were developed for unreliable airspeed events centered on the simple, urgent priority of keeping the aircraft flying before any troubleshooting begins. Recommendations were made about improving pitot probe certification standards, revising the logic in stall warning systems for extreme flight conditions, and upgrading oceanic tracking technology so that an aircraft could never again simply disappear from awareness for hours before anyone noticed. Airbus also became more intentional about how the transition between flight laws was communicated to pilots in the moment, and how training could better prepare crews for the very different aircraft they find themselves flying when the protections step away. The hardest thing about Flight 447 is that it wasn't caused by any single catastrophic failure. It was caused by a chain of small, individually survivable problems that compounded each other in the worst possible sequence, at the worst possible time of night, over the most remote stretch of ocean on Earth, flown by people who were tired and who had never been trained for exactly this combination of circumstances. The lesson the aviation world took away isn't a technical one. It's this: know your aircraft. Not just on a sunny afternoon at 5,000 feet. Know what it becomes when the systems step back. Know what it demands of you when the computers stop helping. And when something goes wrong at altitude, before anything else, fly the aircraft. As long as the wings are producing lift, you have time. You have options. There will always be time to figure out what went wrong after you've secured what's right. If this story stayed with you, hit subscribe. There are more mysteries like this one waiting for you.